thank you for the introduction. So this series of lectures is a sequel of the lectures given last week by Carlo Gasbari. So I will still discuss about algébrisation techniques. And the theme of the lecture is to present various algébrisation techniques that are indeed quite important in the study of foliations in various parallel frameworks, namely in a formal geometry, in analytic geometry, and if time permits, in diophantienne geometry. Okay, so today I would like to discuss some results concerning the algébrisation of some formal subschemes of projective varieties. Well, actually, I will not assume too much knowledge of formal geometry, so I would like to introduce formal geometry through examples. So actually, I will mainly discuss about, let's say, analytic submanifolds. I would like to discuss some very concrete results, let's say in complex analytic and algebraic geometry, and to give the proof. It is quite simple, but if you try to understand the proof in the simplest possible terms, in a sense, you cannot escape to invent formal geometry. So that's the topic of the day. Let's try to invent formal geometry. So let me consider the following setting. Let's consider C in Pn of C. Let's say a smooth projective curve. It's a connected, smooth projective connected algebraic curve. So of course, you know that it is exactly the same thing as a compact Riemann surface, a connected compact Riemann surface embedded as an algebraic manifold in Pn of C. If you already know about algebrisation, you know that compact Riemann surface maybe are always defined by algebraic curves, and that such an holomorphic embedding is always algebraic. Okay, but you can think, okay, it's a very basic geometric data. And assume that you are given, let's say, a germ of C analytic surface through C inside Pn of C. So assume you are given a, let's say, curly V, a C analytic submanifold in Pn of C, C analytic, two-dimensional submanifold. Let's assume it connected to fix ideas. And actually, the only thing I will be interested in is a germ of V along C. I always allow myself to shrink V, provided it still contains C. Okay, so it's some kind of, you have a curve in space, and you have some kind of analytic ribbon around this curve. Okay, so in this situation, you may consider the normal bundle of C inside V. So it's a line bundle you get by, okay, you may give a name to this inclusion morphism from C to V. Let's call it J. Okay, you have, if you want, you may restrict the tangent bundle, the analytic tangent bundle of V to C. And inside this tangent bundle, you have the tangent bundle of C, and you take the quotient. Or more formally, you may consider it is a co-kernel of the differential of G, which maps TC into the restriction of TV. So it is a line bundle over the curve C. And today I would like to discuss the following theorem. If the degree along the curve C of this line bundle is strictly positive, then your ribbon V is algebraic. So let me write algebraic between quotation marks because it's slightly ambiguous. By algebraic, formally, a way to define this, simple way to define this, is to say that if you consider the Zariski closure of V, in the projective space, so it's some closed algebraic subset of Pn of C, and I claim that the dimension of this algebraic thing is 2. So the dimension of the Zariski closure is the same as the dimension of V. It's a definition of algebraicity. It may look slightly not that intuitive. So let me explain why I define it in this way. So comment. What does algebraicity mean? So let's consider a situation, a slightly simpler situation. Assume you are given a germ of analytic curve through a point, let's say in P2 or in A2 on the plane. And suppose you are given a germ of curve C, germ, let's say of C analytic submanifold in the plane of dimension 1. You want to say this germ to be algebraic if it is a branch of analytic curves through the point. For instance, if you take something like this, for instance, a cubic with a double point, if you choose this small piece of curve, you want it to be algebraic. So of course, if you take the Zariski closure of this C, you get the whole cubic. So you see the germ of the Zariski closure through the point is larger than the germ you started with. But, okay, it's very easy, very simple, but you certainly want this germ of curve to be algebraic. But a simple way to define the algebraicity is to say that this C is algebraic. You may take as a first definition that C is a branch of an algebraic curve through O, and it means, of course, this algebraic curve may be supposed to be irreducible, and it has to be the Zariski closure of C, and it's equivalent to the fact that the Zariski closure is one-dimensional. But in general, the inclusion C inside germ of C of the Zariski closure at P may be strict. Okay. So here, in the two-dimensional setting, similar examples may occur. You may have a ribbon that is some kind of two-dimensional branch of a surface that admits the curve as a line of double points. But okay, that's the kind of thing that happens in real life, and you don't want to exclude. Okay. So this is a very simple theorem. Not that well known. Actually, it's due to in slightly more general setting, but to Andreotti, and also rediscovered by Archon. Well, actually, I suspect this theorem in this setting to have been familiar with for somebody like Severi, but I have not been able to find an explicit reference in old Italian literature. But Severi did prove things in this period that are much more intricate, so I suppose for him it was obvious. Okay. So let me give a proof of this theorem. Okay, let us give a name, say S. To this Zariski closure. Well, maybe it's not completely clear that the Zariski closure depends only of the germ of the surface around C. It will become clear in the proof. So let's suppose that you are not given a germ, but an actual submanifold, connected submanifold containing C. And let S be its Zariski closure in PNC, in the projective space. Okay, you need to prove that it is two-dimensional. Okay, how can you describe in concrete terms this Zariski closure? Of course, as any closed subset, an algebraically closed subset of the projective space, you may define it by its homogeneous ideal. So you consider for D a non-negative integer, you may consider ID the set of polynomials in n plus 1 variables that are homogeneous of degree D and that vanish on this Zariski closure. Okay? So of course this it defines a graded ideal in C of x0 xn, which defines S. Okay. Okay, so of course, by the very definition of the Zariski closure, a polynomial P vanishes in the Zariski closure of V, if only if it vanishes on V. Well, so in other words, you may rephrase this definition in another way. In other words, you may say that ID, so ID, by definition, is a set of sections over Pn of the ideal sheaf of S tensor by O of D. So it's a modern way to express this thing. And this is exactly the kernel of the morphism, let me call it eta D, that goes to the homogeneous polynomial, you see as a section of O of D, to, well, you look at the restriction map from a section of O of D over Pn of C to section of O of D, let's say analytic section of O of D along this analytic surface. Okay? Okay, so this is a geometric, let's say, geometric translation using the notion of line bundle of this elementary definition. Okay. So let's say already from this point of view, you see quite easily that this Zariski closure is irreducible. The direct sum of the space of analytic sections along V of O of D So if you have analytic section over V of O of D1 on another one of O of D2, you take their product, it is analytic section of O of D1 plus D2. So this direct sum has a natural structure of graded ring. And it is a domain. Because, okay, the product of two elements of this ring vanishes if only if one of them vanishes, and it's a direct consequence of, let's say, the fact that V is connected, an analytic continuation. Okay, so this proof which is the kernel of a map with range, a domain, is a graded prime ideal. And in other terms, S is an integral subscheme. Is a reducible, if you want. Okay. So let me now arrive to the key point of the proof. The key point of the proof lies in the following two observations. Wow. Okay, using this, you see that anyhow. You look at the quotient, the part of degree D of the graded ring deduced from this graded ideal I. And by this very construction, it embeds by a map induced by this restriction map into the space of analytic function. And you know, it's a basic theory of Hilbert polynomial. The definition of the dimension of a closed algebraic subset, let's say in terms of its Hilbert polynomial, tells you that the dimension of this finite dimensional C vector space grows as this dimension is a polynomial in D of degree the dimension of S. Whenever you are given a closed subscheme of Pn of C defined by some graded ideal whose this part is ID, you may look at the at this sequence of finite dimensional spaces, and their dimension grows like d at the power of the dimension. Actually, it's a Hilbert polynomial. It goes like, it's 1 over factor, let's call this d. It's 1 over factorial d. The degree of s plus smaller order terms. Okay? For d large. So the theory of Hilbert polynomial tells you that for d large enough, this is a polynomial in d. And then that the degree of the polynomial is given by the dimension. And even you can then give the geometric meaning to the leading term. Here, I will need only a very small part of this statement. I need only the fact that it grows like some positive multiple of d at the d. For d large enough for some positive c. Okay, so at this point, you see that to complete the proof of the fact that this dimension is 2, okay, so here it's basically clear that the dimension of the Ricci closure, this is an algebraic subvariety of Pn of C that contains a two-dimensional submanifold. It's very elementary to see that it has dimension at least 2. So this is clear. And so what needs to be proved is the upper bound. So at this point, you see that to prove this algebricity theorem, it's enough to prove key lemma okay, that I will formulate in a more general setting. For any analytic line bundle, let's say L on V, the dimension of the space of analytic sections of the d's power of L over V is finite dimensional, is finite, and is big O of D square. When D goes to infinity. So you see, once we will have proved this key lemma by using this lower estimate. So you see that if D is this dimension, you will get that C, some multiple, will be at most some O of D square by applying key lemma with L, the O of 1 seen as an analytic line bundle with respect to V. If this estimate hold when D goes to infinity, necessarily D is at most 2. let me now give the proof of the key lemma. Okay, the point of the proof is to consider inside V. Inside V, so you have your kind of ribbon, analytic ribbon V, and you have a curve in this, on this complex analytic surface, and you may consider the successive infinitesimal neighborhood of the curves inside the surface. So you have first C, and then C1, the first infinitesimal neighborhood, and in C2, and so on. Successive infinitesimal neighborhoods of C in V. So, by definition, these are, well, except C0, these are non-reduced analytic curves. Technically, you may consider IC inside O and V the sheaf of ideals, current analytic sheaves, let's say, current sheaves of current ideal. Well, current sheaf of ideals. Defining C inside V, and by the very definition, CI is a closed analytic subspace of V, defined by the I+1 power of IC. Okay? So, formally speaking, as a topological space, it is the same thing as C. The set, the underlying topological space of CI is the one of C. But if you are given an open subset, well, but functions are not have nilpotence. O of CI is, let's say, O of V. Okay. So concretely, locally, on New open in V in the analytic topology, and small enough, you may define C by one equation. It's a smooth curve on a smooth analytic manifold of dimension 2, where F is analytic on U. And, well, the differential of f doesn't vanish at any point in C inter U. So in that case, the ideal sheaf of C over U is principal. It's a sheaf of functions that are multiple of f. And if you replace IC by its I plus 1's power, you replace f by f at the power I plus 1. And you see that if you want COI inter U is defined by, let's say, scheme theoretically, but in the complex analytic setting, by the equation f I plus 1 equals 0. Okay, so this may look quite formal, but actually, from this sequence of successive inclusions of non-reduced curves, you get a sequence of space of sections of the line bundle L, or if it's of its this power, L at the power D. So you get a projective system. So let's call it star. From star, you get a projective system of, let's say, finite dimensional C vector spaces. So you may look at the space of analytic sections, say, of L, or L at the D's power. Okay, for simplicity, let me write L, and at the end of the proof, to get the estimate, I will replace L by L at the D's power. Let's write I minus 1 on I. So let me denote this map Q1. So maybe I can write Q0 to 0. This is Q2. And this is Qi. So the maps Qi's are the pullback by this successive inclusion map. So an element here in this space, gamma CIL, is a section of this line bundle L over this non-reduced curve CI. And you may restrict it to CI minus 1. That is a slightly less reduced curve, non-reduced curve. OK. So at this stage, let's say we may define gamma of V at C, the formal completion of V along C of L, defines this as the projective limit of the spaces. So by its very definition, by the very definition of the projective limit, an element of this projective limit is a sequence of successive sections of L on the successive thickenings, Ci of L, that are compatible. Each one has to restrict to the previous one. Okay. Okay, so I would like to make two observations. That will actually lead very directly to the proof of this key lemma. The first observation is that you have some kind of obvious restriction map from the space of analytic section of L along your analytic region V to this projective limit. It's very easy to define. If you take an analytic section of L along the two-dimensional manifold V, of course, for any I, you may restrict it to the curve Ci, and this family of restrictions are trivially compatible. So you get an element here. So I claim that this map is injective. And the second observation is that for any I, the kernel of the map Qi may be identified with something quite concrete. The section along the curve C, the reduced curve we started with, of the line bundle L restricted to C, twisted by the dual of the normal bundle of C in V. You take the dual of it and you take it at the ith power. And of course, this space is finite dimensional. It's the space of section of this line bundle on this curve. And it's very easy to get some upper bound on the dimension of this space. So let's say the trivial part of the Riemann-Roch formula, the Riemann's inequality. This, if the degree of this is negative, it is 0. If it is positive, it is at most 1 plus the degree, by very elementary consideration. So this proves that this dimension is at most, let's say, the positive part of 1 plus the degree of that, which is the degree of L, minus I degree. Okay. Okay. So, well, in a sense, these two assertions are very easy, and it's also very easy to see that they imply the key lemma. So let me first explain how you go from these observations to the key lemma. So to bound of course, you may apply this key lemma to L at the power D. To bound the dimension of this space, it's enough to bound the dimension of this one. So you say and now, you use this second observation on the fact that the degree of the normal bundle is positive. So you see, when L is given, when I is large enough, the degree of this becomes negative. So this space becomes 0. This dimension becomes 0. So for E large enough, depending on D, K of Qi is 0. So it means that all the maps Qi's are injective. So it proves that the dimensions, the sequence of dimensions of the gamma Ci L is non-increasing. So these dimensions, of course, are finite numbers. So this sequence becomes stationary. And then once the maps are injective, the dimensions are all the same. All the Qis are isomorphism. And you see, at the end of the day, that this space may be identified with the space of sections. The projective limit may be identified with the space gamma Ci L for I very large. It's a kind of stupid projective limit. It's stationary. It's an eventually constant system. On the dimension, so again, on the dimension you are interested in is the dimension of this for I very large. And this dimension is at most the sum of the dimension of the successive kernels. I started with Q0, which is 0, so I suppose it starts with 0. So it's at most this. Well, actually, it's a finite sequence. 1 plus degree of L that I replace by degree of LD. So it's and I claim that this goes like O of D square, so it's basically clear. So let me draw a picture. So you are given D, and you look at this as a function of I. So it starts at 1 plus D degree L, and then it decreases with a slope minus this degree, and you count the number of integral points inside this, something So it's clear that it goes like this square. Okay. Okay. So you are done, provided you have proven these two observations. Okay. So let me prove these two observations. Okay, let me first prove the first observation. Actually, this map is injective because it's basically clear. Actually, much stronger statement is true. Just pick any point P in the curve. And what I claim is that, okay, if you are given S, an analytic section of L, the sequence of the restriction of S along the second curve actually determines the Taylor expansion of S at P. And by analytic continuation, if this Taylor expansion is 0 at one point, the section has to be 0. So let me explain this, maybe in concrete terms. For instance, locally, you have your point P. You may choose two analytic coordinates. On V, such that C is given by y equals 0. So Ci would be given by y I plus 1 equals 0. You may assume that L is locally trivialized, it's a trivial line bundle. So you see a section, a function, so locally at the level of germs, section, maybe I should already explain this. Gamma CIL is, of course, the space of section of L ICIL by the very definition. And this is like a function quotiented by this sheaf of ideal. So at the level of germs, it's like convergent series in two variables, quotiented by so it's the same. This is the same thing as the direct sum of I copies of, let's say, K from 0 or I plus 1 copies of convergent series in one variable. Okay. So you see that if a function has its image in all the expressions 0, it means that the Taylor series in two variables is 0. So it's each. Okay, you see this physically in coordinates. Okay, this proves the first observation. On the second observation, How do you okay, I just want to be sure I don't forget anything. Okay. So by definition, as I explained, O of Ci so let me work in analytic geometry. Like this. And the restriction of L to Ci is let me, by the same letter L, the sheaf of analytic section of L. So it's L. Okay. So now you see that IC, quotiented by IC square, so it corresponds in this notation to, at the level of germs, so if you want, it corresponds to a line bond that is scaled by EI of C. It's a current sheaf that is scaled by I sub C. So you may identify this to a current sheaf of C, and it's the same thing up to the immersion G. Have the normal bundle, dual of C in V. So you have a canonical map here, which locally in coordinates is given by this formula, which doesn't, of course, it doesn't depend on the coordinates. So you may explain this. Here you take a function, a section of a function f that vanishes along C at zeroth order, well, that vanishes along C, and you associate to this function its differential along C as the sections of the normal bundle. So this map is well defined because if f is in IC square, its differential is 0. And once you know it is well defined, you compute it at the level of germs by this formula to see it is an isomorphism. So you get this canonical isomorphism. And in the same way, you see that ICI quotiented by ICI plus 1 may be identified by the line bundle. Here again, it's a current sheaf that is supported by C. It corresponds to current sheaf over the curve C, and it corresponds to the highest power of the dual of V. If you want, you take a function f that vanishes to ith order along the curve, and you look at its Taylor at the ith term of its Taylor expansion, the first possible non-vanishing term, and it gives you an element of this. Yes. Yes. Along C. Okay. So you see, this isomorphism are basically determined by these ones, in the sense that you may consider the direct sum of these quotients, and it's by looking at the various. Okay, you get the sum of this canonical isomorphism. You get the direct sum of these things. On both sides have a natural structure of algebra. By look at the definition, this is a symmetric algebra, and this is a quotient by, and this is an isomorphism of algebra. Okay, just take one second to complete the proof. Okay, you have the successive inclusion of the infinitesimal neighborhoods ci minus 1 into ci at the level of morphism of sheaf of you get a surjective map by restricting a function there to a function of c minus 1, and by definition the kernel is exactly this space. I need to be. Okay. Here, this is the kernel by the very definition of O of Ci of C minus 1 as a quotient. And this kernel is this sheaf. So it means that the kernel operates a current sheaf supported by Ci, but actually it's not supported in the whole thickening. It's supported by the curve C itself. And it's given by this line bundle. And now you may transfer this by L, and you get LCI. And here you get L restricted to C, well, L tensor and this of course is the line bundle, the current sheaf defined by the line bundle obtained by taking the restriction of L and twisting it by the highest power of the dual of the normal bundle. And from this, of course, from this exact sequence of sheaves, you get an exact sequence of space of sections. Oh, minus 1. So from here, you get well, it's not a long exact sequence. You get naive exact sequence corresponding to the fact that the space of the functor of sections is left exact. You don't need to know anything about cohomology in this proof. And means that the kernel is exactly what I claim it is. And the proof is complete. Okay? Okay, I have to stop here.